Hello, everyone. Welcome to our lecture on informed search methods. In the previous lecture, we were looking at uninformed search methods, where we did look at algorithms such as breadth-first search method and depth-first search methods. Now, what we said about search in general is that when an agent is trying to solve a problem, it will formulate this problem it will formulate this as a search problem where it's going to list the state space, the operators, the initial state, the goal test, the path cost, the cost function, and the transition model. So those are the things that will be listed in defining the search problem. After the search problem has been defined, the process of finding a solution, of the process of moving from the initial state to the goal, we'll go through the process of searching for a solution. Now, in the first category of search methods which we looked at, the uninformed search methods, which we were also referring to as blind search methods, what we said was the agent has no extra information about the problem domain. So what it will do is it will just search the state space for a solution. This, in comparison with the other method which will be talking about today, is time-consuming and in many cases inefficient. On the other hand, we have informed search methods. In informed search methods, there is additional information about the problem that the agent will have. So the agent will have some extra information about the problem domain, and that's what it will use to find the solution. So usually what the agent will do is, using the information it has about the domain, it's going to concentrate on those parts that are more promising, thus reducing the search time. Just to give a picture of what we're trying to say here. Imagine we have an agent, a self-driving vehicle that's supposed to move us from Kitwe to Lusaka. If the agent is using an informed search, it doesn't know where Lusaka is. It doesn't have any extra information. So it will just keep searching until it finds a solution. This solution may not be the most efficient. It may not be the most efficient, but it as long as it gets us to the goal, that's well and good. If the agent is using informed search methods, it will have some extra information. For example, the extra information could be something like Lusaka is south of Kitwe. So what the agent will do is it will start by looking at those towns which are south of Kitwe, because it knows that they are taking it closer to the goal, which is to reach Lusaka. So there is that extra information that we have. So the extra information is what we are referring to as heuristics. Now, this heuristic, or basically it's a rule of thumb or an estimate, something that will help us to look at how good or how promising a path is. Usually, this will be given by a function, the heuristic function, and it will provide an estimate of the cost of the path from a given node to the closest goal state. That's what we are trying to say. So basically, there will be some estimate. Shortly, we'll see an example so that we can consolidate this. Now, the heuristic or why do we want to use these heuristics? We want to find solutions efficiently. Imagine you are playing a game against an intelligent agent. Let's say you are playing chess, And then this agent maybe is taking 2 hours to make a single move. So each time you make a move, it has to start searching for the solution to look at which path is more promising so that it can win the game. And it's taking maybe 2 hours. The game will be very boring and we'll end up just abandoning it. Because what we want is we want the game to be done within some reasonable amount of time. So what we want is efficiency, hence the inclusion of these estimates. So the estimates will just help us to have an idea of how close a particular state or a particular node is to the goal. We'll now talk about heuristic search methods, and we'll pick on one group of heuristic search methods, that is the best first search methods. Okay, now in the best first search methods, what we are trying to do is we want to consider those nodes that are more promising. So when we have that estimate, remember we're just talking about the heuristic function and the estimate to the goal. When we have a state that is more promising, we're saying consider that one first. Consider that one first. So you look at all the states that you have, then you check which one is more promising. When you find the one that's more promising, that is the one that you expand. So that is what we are trying to say here in this on this slide. So we're saying heuristic search is a type of algorithm that is used to find the best solution to a problem using some heuristic function. Now let's look at the general search algorithm, which uses this best first search algorithm. So what we are saying is we are going to create a list. We're going to create a list which we are calling fringe, which will be a priority queue containing the initial state. So the first step, we're saying get the initial state and then perform the following actions repeatedly until we run out of nodes. So the first thing, you look at this fringe. Now, recall when we're talking about the search tree, we had talked about fringe nodes, we had talked about open nodes, we had talked about closed nodes. The open nodes, we had also referred to them as fringe nodes. Now, these fringe nodes, we're saying they contain or they are yet to be expanded. And we said the goal state will be one of these fringe nodes. So any node that is not expanded yet is a fringe node. So we are going to consider these fringe nodes. So we have this list of nodes that are not expanded. So we're saying get the first node. If that node is a go, then return a path to that. You found your goal. So now you're saying, how did we move from the initial node to that node? If it's not a goal, then we're going to look at the successor nodes, and then we're going to put them according to their estimate value. Don't worry, we'll look at an example very shortly to make sense out of this. So this general search method, okay, yields a whole family of methods, which we are calling the best first search algorithm. Now, best first search algorithm, we have two kinds, or we have two approaches to searching. When we are searching, we could look at from where I am or from where the node is, how far is it to the goal? So that is the first approach. You look at from a particular node, you look at how far or how close is it to the goal. When you're driving between towns, you usually see an estimate. Let's say as you're driving from Kitwe to Lusaka, When you get to Ndola, or as we're exiting Ndola, there is an estimate to say to get to Kabwe, it's about maybe 200 kilometers. To get to Lusaka, it's about 353 kilometers. That's from Ndola. As you get to Kapiri, it will tell you to say the estimated distance to Lusaka is about 300 kilometers, something like that. As you get to Kabwe, the estimate to Lusaka reduces, maybe it's about 250. Similarly, if you are coming from the northern part of Zambia, let's say if you get to Serenge, to Serenge, they'll tell you to say from Serenge to Lusaka, the distance is about, let's say 600 kilometers. You get to, Serenge to Lusaka, 600 kilometers. If you're coming from the south, Livingstone to Lusaka, when you get to Choma, they tell you that from Choma to Lusaka, it's about maybe 450. So now imagine that's our state space. We have Serenge, we have Kabwe, we have Choma, each with its own estimate distance. So we're saying we are going to go for a state that is closer to Lusaka. So that would be Kabwe. In a short while, we'll look at an example and this will make sense. So don't worry. So sorry. The first approach we're saying, we are going to look at a node and we are going to, as we are selecting the nodes to expand, we are going to go for those nodes that are closest to the goal. The nodes that are closest to the goal are the ones we are going to consider. That is the first approach. In the second approach, we are going to look at the node which has the lowest path cost. The lowest path cost, that's the one we are going to take. So there are two approaches. In the first approach, we're saying when we're looking at the nodes, we don't care how it has moved, how we have moved from the initial state up to that node. We are just concerned to say, now we are in this node. How close are we to the solution? That is the first approach. In the second approach, what we are trying to do is we are asking ourselves, what is the cost to get to this node? Plus, how far are we from the goal? So we are concerned with the entire path cost, and what we want is to get the least cost solution path. That's what we will look at. So let's look at the first approach. The first approach tries to minimize the cost to reach the goal. And this particular method is referred to as the greedy search. So when we talk about greedy search method, we're talking about informed best first search method, which uses the estimated cost, from that node to the goal state. That is the idea. So in greedy search, what do? We are going to have our state space, and in the state space, there will also be some estimate. There will be some estimate to say from this goal or from this state where you are to the goal. This is how long it will take. Like this is the estimated cost. And what we are going to do is we are going to expand those nodes that are more promising. So the node with a smaller cost is preferred. So let's look at an example and then use that example to solidify what we are trying to explain here. So we have this map of Romania, which we've already seen, and we have been given a question here. It says, the figure below shows a simplified map of Romania. The distance between towns is shown on the map. So for example, from Arad to Zirint is 75 kilometers. Let's assume they are using kilometers. From Arad to Timzwara, it's 118 kilometers. Then the straight line distance from Bucharest is shown on the side of the map. So here we are looking at the estimate. Remember the goal, we want to move from Arad to Bucharest. From Arad to Bucharest, that is where we want to move. Now, each of these, we are trying to look at how close it is to the goal. So remember, we said in informed search methods, there is an estimate. There is an estimate. We should have some estimate of how far each node is from the goal. So for example, the estimated straight line distance from Arad to Bucharest is 366. Bucharest has the estimated distance from Bucharest to Bucharest is 0, meaning you've already reached your goal. So when a question like this is given and the goal state is not indicated, you look at these estimates. The goal state will always have a 0. Why? Because we know that when you've reached your goal, there's nowhere else you are supposed to go to move to. So that is the idea. So each of these towns has a straight line distance, which is estimated. So when we have a situation, as we are going to see very soon, when we are trying to pick among the children of a particular node, we are going to look at one that is promising. Let's start. If we can just think back to the generic algorithm, we said, okay, let me just go there. We said, let's have a fringe. Let fringe be a priority queue which contains the initial state. And when we have this initial state, so let me just annotate something. Okay. So we want to show the working. Okay, let's see. Sorry about that. Okay, I don't even know what color this is or why I picked it up. Why? Okay, yeah, so all right. So we have these different terms. So okay, so just a second. Okay, so I'm going to just put up something here. We want to show the working. Now, in showing the working, we are going to maintain two lists. The first one is the open list, and the second one will be a closed list. In the open list, which we are calling the fringe, that is where we are going to keep the list of states that are yet to be expanded. So when we start, initially, we are going to have Arad as the only state that we have. Then on the closed list, remember those nodes which have already been expanded, we don't have anything at the moment. The algorithm says get the first element in the open list, that is the fringe, in fringe. So we have Arad. We ask ourselves, is Arad the goal? No. So when we see that Arad is not the goal, what are we supposed to do? We expand Arad. So if you just recall the way we were doing it last time, we said from Arad, the possible areas we can go or the possible towns we can move, the children of Arad are Sibiu, Timzora, and we have Zerit. That's what we had said. Now, In this case, with informed search methods, what we do now is we are told to say, these children, you should order them according to the estimate. So the preference, the node that is more promising is supposed to appear first. So if you look at the towns that we have Sibiu, we have Zirint, and we have Timzora. So now let's look at here. Zirint has an estimate of 374 to get to the goal. So meaning the straight line distance from Zirint to Bucharest is 374. Then Timzora is 329. Sibiu is 253. So Sibiu is closer to Bucharest, meaning it's more promising. It's more promising. Then the second one, in terms we're trying to order them, is Timzora, and Zirint is the last. Okay. Then in the closed list, that's where we are going to take Arad. Why? Because we've already expanded it. Now, from these children of Arad, the next step that we now take, we look at which one is promising. It's Bill. So now, you, according to the algorithm, check, is Sibiu the goal? No. So what we now do is we move Sibiu to the closed list. So in the closed list, we now have Arad and we have Sibiu. Then in the open list, what we now do is we have to expand, or we have to take into consideration the children of Sibiu. Who are the children of Sibiu? There is this, which I'll just call RV. Then this one is Fagaras, then Oradia. Okay, so in putting this, in ordering this, you need to put them in order of distance. The closer ones are the ones that you put at the beginning because they are more promising. Okay. Okay, they are more promising. So I hope I'll still be able to come back to this. Okay. Okay. Yeah. So what I'm trying to say is when we're looking at Sibiu, we said the possible towns we have are Oradia, we have Ferrara, and we have RV. Okay, so now with this, what we now want to do, sorry about that. Okay, so let me just, okay, all right, yeah. Okay, so let's go to, let's just work backwards with this. So initially we started with Arad. This is where we are. And when we checked that Arad was not a go, we expanded Arad. We expanded the open node by including the children of Arad, who are Sibiu, Timzora, and Zirint. Now, when we expanded Zirint, this is now a closed node. That's why I brought it here. After I brought this one here, I now have the children of these three children. So now I'm going to consider the child who is more promising, and that's Sibiu. So with Sibiu, I check, is Sibiu the goal? It's not. So now I take Sibiu here because I've considered it. Now, in this open list, what I'm now going to do, I'm going to put the children of Sibiu together with the sibling of Sibiu, and I'm going to order them in accordance to the distance, the estimated distance. So we know that Zirint is 374. We know that Timzora is 329. How about Oradia? Oradia is 380. So 380 is actually beyond Zirint. So Oradia will be at the end, unless we see something bigger. Then we have Zirint. Okay. So the other one we have is Ferrara. So Ferrara is about 178. So from the ones that we have, okay, from the ones that we have TZ, Oradea, Ferrara, RV. So from the list that we have, Ferrara is more promising. Okay, so Ferrara is more promising. Yeah, sorry, my mouse has gotten stuck, has got stuck. So let me just clean this up and then work through it. Okay, anyway, let me just explain and then I'm going to do the writing. So we are saying order the children in accordance with how close they are to the goal. So that is the concept that we are working with. So let me just clean everything here and then start all over without having to draw this. I hope you'll be able to follow. Yeah, so initially in the open list, we just have a rent, and in the closed list, we don't have anything. Now, once we see that Arad is not a goal, we are supposed to add the children of Arad, who are Sibil, Timzora, and Zirind. Now, you arrange these in accordance with the distance. The one that is closer to the goal, that's the one that you list first. Why? Because we want to expand the more promising nodes first. Once we do this, the next step is we look at the remaining sorry, the remaining nodes in the open list. So we check Sibyl. Is Sibyl the goal? No. So what do we do? Sibyl will be taken to the closed list, and we are now going to add the children of Sibyl to the open list. Who are the children of Sibyl? Orara, Oradia, Ferrara, and Aravi. So we are going to order them in accordance with their straight line distance. So the one that has the smallest distance is what appears first. So now let's look at Timzora. We know that it is 329, Zirind 374, Oradia is 380, Ferrara is 178, RV is 193. So 178 is the more promising one. So we have Ferrara being listed first, followed by RV. Okay, followed by RV. And then we, okay, Oradia is 380, so which is much further than the other ones. So we look at Timzora and Zirind. Timzora will be the third one. Okay, so I'm ordering this in accordance with the straight line distance, the estimated distance to the goal. Okay, so this one, then Zirind, and then the last one is Oradia. So in this order, you find that this one is furthest from the goal. Then in the closed list, we now have Arad and Sibyl. When we get to this point, we look at Ferrara. Then we ask ourselves, is Ferrara the goal? No. So we are supposed to expand Ferrara by including the children. Who are the children of Ferrara? The children of Ferrara are Bucharest. So we will take this, we'll take Ferrara to the closed list and then add its child, Bucharest. Now, what is the cost of Bucharest? It's 0. So this one has the shortest distance, Bucharest, and then the other two will remain this. The other nodes will remain the same. The order will not be changed. Okay, like that. Then in the list, we now have Arad, Sibyl, Ferrara. Okay. We continue. We get the node that has the shortest distance, Bucharest. Then we ask ourselves, is Bucharest the goal? Yes. So meaning in the open list, it will remain with that Timzora, Zerid, Oradea, yet to be expanded. And because we've taken Bucharest to the closed list, meaning we have considered it, we have now reached our goal. If anything, we shouldn't even call it an open list. We shouldn't even take it here because we know that it will have no children. It will still be a fringe node. So basically, what we have is in the closed list, we have Arad, Sibyl, Ferrara, and then we have reached our goal, which is Bucharest. Yeah. So once we get this, once we expand this, we know that we now have on this end the nodes that we've considered are. I want to keep them away from this list so that I don't confuse you. So we have Arad, we have Sibyl, we have Ferrara, and we have Bucharest. So the question that we are trying to answer is, what is the order that grid search will expand this node? And that is our answer. I hope this is clear. So the whole idea with grid search method is it will look at the estimates and it will go for those states at any point. It's going to get a node that is more promising. That's what it will take. It is not checking. This method is not checking how far we've come from the initial state. What is the cost from the initial state? It's just looking at from where we are up to the goal. How far are we? We are not looking at where we're coming from. We're just focusing on where we're going. So that is the idea of grid search method. That's the idea of grid search method. So I'm going to stop here for now. And in the next video, we will now look at the second part of this informed search methods. And that is where we are looking at the path cost now. So that's what we are going to look at in the next video.